Let me tell you something that took me a long time to understand. Scientists are not fearless. I know that is not what we are taught. We grow up with this image of science as the brave enterprise, the one human activity that follows the truth no matter where it leads, that tears down sacred cows without hesitation. In the next few years, science has done things that required unsacred territory, but the consequences of the university are unsacred, and people are more likely to train the quality of the individual. The two individuals are petty or petty. It displaced the Earth from the centre of the universe at a time when the alternative could get you burned. It showed that humans and apes share a common ancestor in an era when that claim cost people everything. It revealed that the rock beneath our feet is floating on a churning sea of molten mantle, which was considered insane by the geological mainstream for decades after the evidence was already clear. Those were real fights, not abstract disagreements in journals, real fights where real people had their reputations destroyed and their funding pulled and their work dismissed by the institutions that were supposed to protect honest inquiry. But there is a different kind of courage that science is less good at. The courage to sit with a question that doesn't have an answer, not the patience to wait for data. Science is good at that. The courage to sit with a question that implies the foundations are wrong. The courage to follow the mathematics honestly into the places it leads, and then publish what you find, even when what you find suggests that the thing everyone else built their careers on top of is built on sand. That kind of courage is rarer, and the absence of it creates something specific. It creates silence, not ignorance. The people who know about these theories are among the most technically sophisticated researchers in the world. Not dishonesty. The papers are published, the data is available, the arguments are there for anyone who looks. Just silence. The institutional, collective, unspoken silence that forms around ideas too large to discuss safely. Ideas where the implication is not this phenomenon needs a new explanation, but this foundational assumption we have been using for decades might be wrong. There is a recognizable texture to this kind of silence. The papers exist, but accumulate very few citations. The problem gets acknowledged in a footnote, and then the chapter moves on. Senior researchers at conferences change the subject. Funding agencies categorize the question as philosophical rather than empirical and decline to support it. Tonight, we are going to go to exactly those places, 10 of them. Every single theory we discuss has been formally published in peer-reviewed journals by researchers at credible institutions. Every single one is backed by data or mathematical arguments that have not been disproven. And every single one, if correct, does not just add to the picture of reality, it changes what the picture is of. Let's start at the very beginning. The most personal version of the most fundamental question. Here is the question I want you to sit with before I explain anything. Why are you made of anything at all? Not what are you made of? Not how did the atoms in your body assemble into this particular configuration? Why is there matter in the universe at all? Why didn't everything cancel out in the first second and leave nothing behind? Because according to the most precise and well-tested physical theory ever constructed, it should have. The matter that makes you up, every proton, every electron, every atom and every cell should not be here. It should have been annihilated in the first fraction of a second after the Big Bang, before the universe was old enough to be called the universe. And the reason it wasn't is something we completely, totally honestly do not understand. Here is the physics. The Big Bang created the universe as an explosion of pure energy. As that energy cooled in the first fractions of a second, it condensed into particles. And here is the thing that matters. It made them in pairs.
For every particle of matter that formed, an equal particle of antimatter formed alongside it. Proton and antiproton, electron and positron, matter and antimatter, born together, existing in perfect balance.
This is observed every time we collide particles in an accelerator today, every experiment at the LHC, every measurement at Fermilab. We see it happen. Particles are born in pairs, matter and antimatter, one of each, created together. Now think about what happens when matter meets antimatter. They annihilate. They cancel each other out completely. They convert back into pure energy. A proton and an antiproton collide, and they become two photons of light. Nothing is left. No proton, no antiproton, no debris, just light. So run the Big Bang forward with this knowledge. An explosion of energy creates particles in pairs, matter and antimatter in exactly equal amounts, all in the same place at the same time, all moving at merely the speed of light, slamming into each other almost immediately. The matter meets the antimatter. They annihilate. Everything converts back into pure light. The light spreads outward into the expanding universe, cools to nothing, and the story ends before anything interesting can happen. No galaxies, no stars, no planets, no atoms, no chemistry, no biology, no you. A universe that begins with perfect symmetry between matter and antimatter should end with perfect emptiness. But you exist. You are reading this on a screen made of matter. The screen is sitting in a room made of matter. The room is on a planet made of matter. The planet orbits a star made of matter. The star is in a galaxy made of matter. The galaxy is in the universe, the entire visible universe, 93 billion light years in every direction, that is made almost entirely of matter with virtually no antimatter. Something broke the symmetry. Somewhere in that first fraction of a second, the balance was violated. Matter won. Not by much, not by any large margin. For every billion matter-antimatter pairs created in those first moments, there was one extra particle of matter. One. Not 1,000, not 1,000,000. One lonely extra particle for every billion pairs. The billion pairs found each other and annihilated, their energy dispersed as radiation. And that one extra particle, that rounding error, but 1 in a billion deviation from perfect balance, survived. Everything you see in the night sky is made of those survivors. You are made of those survivors. The entire visible universe, every galaxy, every star, every planet, every atom, is the debris field left over from a tiny asymmetry in the first second of time. We are rounding errors. We are the leftovers. We are the 1 in a billion accidents that the universe didn't clean up. And we spent centuries building civilizations, writing philosophy, doing science, and asking questions, without ever being told that none of us should be here. Now here is where the silence comes in. We have a theory called the Standard Model of Particle Physics. It is the most precisely tested theory in the history of science. Not one of the most precisely tested, the most. The anomalous magnetic moment of the electron, a tiny quantum correction to how electrons behave in magnetic fields, has been predicted by the Standard Model and measured experimentally to 11 decimal places. The agreement is perfect. No other theory in any scientific discipline has been verified to this level of accuracy. And the Standard Model cannot explain why you exist. The Standard Model contains matter-antimatter asymmetry. It is built in through something called CP violation, a small preference for matter over antimatter under certain conditions. We have measured this CP violation in particle accelerators. We have confirmed it is real. But when you use the Standard Model to calculate how much asymmetry was produced in the early universe, when you run the numbers on how much extra matter was created for every billion pairs, you get a number that is billions of times too small. The Standard Model's CP violation produces a universe that should be far emptier than ours. The asymmetry it predicts is nowhere near sufficient to explain the amount of matter we observe. Think about what that means. The theory that correctly predicts the magnetic moment of the electron to 11 decimal places cannot explain why there is matter in the universe at all.
Our greatest achievement in theoretical physics has a gaping hole at its centre, and the hole is not in the details, it is at the foundation. It is in the answer to the question, why does anything exist?
This problem is called baryogenesis, or the matter-antimatter asymmetry problem. It has been known since the 1960s. It is in every textbook on cosmology and particle physics, mentioned in the opening chapters where the big unsolved problems are acknowledged, and then quietly set aside while everyone goes back to calculating things that assume the matter already exists. There are proposals, there are extensions of the Standard Model that introduce additional CP violation. There are theories involving new particles we haven't detected, new symmetries we haven't observed, new processes operating at energy scales our current accelerators cannot reach. None of them has been confirmed. None of them is the answer. And the question, why does matter exist at all, sits there in the open, acknowledged by everyone in the field, solved by no one. We are living inside a mathematical impossibility, not approximately inside one, not in the neighbourhood of one, inside one. The matter that makes up your body exists in direct contradiction to the predictions of the best theory we have. Every breath you take is an unsolved problem. Let me tell you about a physicist who helped build the mainstream model of cosmology and then concluded that one of its most fundamental assumptions might be wrong. Andreas Albrecht is a professor at the University of California, Davis. In the 1980s, along with Paul Steinhardt, he developed one of the key versions of inflation theory, the idea that the universe underwent a period of exponential expansion in its first tiny fraction of a second. Inflation is not a minor detail of cosmology. It is a central pillar. It explains the large-scale uniformity of the universe. It explains why the geometry of space is flat. It explains the specific pattern of temperature fluctuations in the cosmic microwave background. Inflation is in every textbook. Albrecht helped put it there. And then, in the late 1990s, Albrecht published a series of papers with Joanne Magejo, a physicist at Imperial College London, arguing that the speed of light was dramatically higher in the early universe, not slightly higher, possibly orders of magnitude higher, possibly approaching infinity at the very beginning. Why would someone who helped establish inflation then argue for something that threatens it? Because there is a problem at the heart of inflation that its proponents are reluctant to advertise. To understand the problem, you need to understand why inflation was proposed in the first place. Look at the cosmic microwave background. The oldest light in the universe, the faint glow of radiation left over from when the universe was about 380,000 years old. Map it across the whole sky. You will find that it is extraordinarily uniform. Everywhere you look, the temperature is the same to 1 part in 100,000. This uniformity is a puzzle. The regions we see in opposite directions of the sky are billions of light years apart. Given the speed of light and the age of the universe, they have never been in causal contact. No signal has ever travelled from one to the other. They are, in a technical language of physics, outside each other's causal horizons. They should have no way of knowing about each other, and therefore no way of reaching the same temperature. And yet they are at the same temperature. Inflation solves this by saying that before the expansion, everything was in a tiny connected region. That region equilibrated firmly. Everything reached the same temperature because everything was close enough to exchange energy. Then inflation stretched this tiny equilibrated region out into the vast universe we see today. The uniformity is a fossil of the original thermal contact. This is a clean solution. It works. But it introduces something uncomfortable. Inflation requires a hypothetical scalar field, the inflatum, that has never been detected. It requires this field to turn on at a specific moment, for no specified reason, and turn off at another specific moment, for no specified reason. The parameters of inflation, when it starts, how long it lasts, how much it expands space, have to be tuned carefully to reproduce the universe we observe. And there is no deeper physical principle that fixes those parameters. They are just inputs. Migejo and Albrecht's alternative: what if the speed of light was simply higher in the early universe? If light could travel faster then, the regions that appear causally disconnected today were in genuine thermal contact at early times. They exchanged energy, they reached the same temperature. Then the speed of light dropped to its current value, locking the universe into the equilibrated state we observe. The varying speed of light theory makes the same prediction as inflation about the uniformity of the cosmic microwave background, and does it without a mysterious inflaton field that has never been detected. More importantly, it makes specific quantitative predictions about the spectral index, a number that characterizes the pattern of temperature fluctuations in the background radiation. Inflation predicts this number, but with a free parameter that has to be tuned. The Migejo-Albrecht version predicts it from first principles, and some of their predictions were borne out by subsequent measurements. Now here is why this goes beyond a technical dispute. If the speed of light has changed, if c is not an eternal constant, but a value that evolved as the universe cooled, then every equation in physics that contains c needs to be reconsidered. That is, most of them. E equals mc squared, the Maxwell equations of electromagnetism, the entire framework of quantum electrodynamics, the relationships between all the fundamental constants, because many of them are related to each other through c. More deeply, if c can change, then what we call the laws of physics might not be universal, eternal truths. They might be the current equilibrium values of physical fields, values that settled to what they are as the universe matured, that were different at the beginning, and that might vary across regions of the universe we cannot observe. This is a much bigger claim than we need to update a number in an equation. This is a claim that the fixed, eternal character of the laws of physics, one of the deepest assumptions of the scientific project, might be wrong. The mainstream has largely continued to develop inflation rather than VSL. This choice is not made purely on scientific grounds. Inflation has decades of investment. Thousands of papers have been written on it. Major careers are built on it. Funding agencies have supported whole research programs around it. To seriously entertain VSL would require acknowledging that all of that work was built on an assumption, the constancy of C, that might not be correct. This is the institutional inertia that protects all paradigms, regardless of their merits. But let me push further, because the implications of VSL go beyond cosmology. They go into the architecture of the laws of physics themselves. When physicists talk about constants of nature, they mean values that are fixed, not just fixed in practice, but fixed in principle. They are not outputs of any equation, they are inputs. You put them in at the beginning, and everything else follows. The speed of light, the charge of the electron, the gravitational constant, Planck's constant. These are the dials on the machine, and the machine has no mechanism to change them. But here is the thing about dials. Someone put them in a specific position. The fact that they are in the positions they are is not explained by any physical law. It is a brute fact about the universe we were born into. If C could vary, if it was a dynamic field with a value rather than a fundamental fixed quantity, then it is not a dial at all. It is an output. Something determined it to be what it is. Some physics, operating in the early universe, drove C to its current value and held it there. And the question becomes, what physics, what froze the speed of light? That is a question with an answer we could, in principle, find. It turns an unexplained input into an explainable output. This is actually a more scientifically satisfying structure than a list of arbitrary constants, but it requires admitting that the constants are not constant. And admitting that the constants are not constant requires admitting that every equation built on their being constant, which is all of them, is potentially missing the terms that account for their variation. We are possibly using incomplete equations to describe a universe whose fundamental laws evolved, and calling the outputs of those equations constants, because we built the equations at a time in the universe's history when the evolution had already stopped. The speed of light might not always have been what it is today. And if it wasn't, the implications ripple outward through every equation we have ever written, and backward through every conclusion we have drawn from those equations. This is the one that makes physicists deeply uncomfortable at parties. Not because it's obviously wrong. Because if it's right, it means that science as we practice it, the idea of an objective observer studying an objective reality, is built on a mistake. Here is the core of quantum mechanics, stated as plainly as possible. Particles do not have definite properties until they are measured. An electron does not have a definite spin, up or down, until something interacts with it and forces it into one state or the other. Before the measurement, the electron exists in a superposition, a mathematical combination of both possibilities simultaneously. This is not a statement about our ignorance of the true spin. The equations say the electron genuinely has no definite spin. It is in both states at once, in a mathematically precise sense. Then you measure it. The superposition collapses. The electron is now in one definite state. The measurement produced a definite outcome. The question that has been open since 1927 is, what causes the collapse? The equation that governs how quantum states evolve over time, the Schrödinger equation, is perfectly smooth, perfectly deterministic, and contains no collapse. It says that superpositions evolve into larger superpositions. Run it forward and you get more superposition, not less. The Schrödinger equation never produces a definite outcome. Collapse is added to the theory as a separate rule, imposed by hand, because without it, the theory would predict things we never observe. But the Schrödinger equation doesn't tell you when to apply the collapse rule. It doesn't tell you what counts as a measurement. That distinction between a measurement that collapses the wave function and a physical interaction that doesn't is not in the mathematics. It is assumed. John von Neumann, one of the primary architects of the mathematical foundations of quantum mechanics, a person of extraordinary technical ability, made foundational contributions to mathematics, physics, computer science, and economics simultaneously, examined this question carefully in 1932. He traced the chain of events in a measurement from the particle being measured, through the measuring device, through the environment, through the readout, through the human visual system, into the brain of the observer. At every step in the chain, he found the same structure. The measuring device is made of quantum particles. Those particles are governed by quantum mechanics. So the measuring device, during the measurement, enters a quantum superposition entangled with the particle being measured. The readout on the device is a quantum state. The photons travelling from the readout to your eye are quantum. The photoreceptors in your retina undergo quantum mechanical transitions when they absorb those photons. The neural signals travelling up your optic nerve are electrochemical processes governed by quantum chemistry. Every step in the chain is quantum. There is no natural boundary where the quantum world ends and a classical world begins. And because there is no boundary, the superposition never naturally terminates within the physical chain. From Neumann's conclusion, stated carefully and without mystical intent, was that the chain terminates at a conscious observer. The wave function does not collapse when a particle hits a detector. It does not collapse when a readout is generated. It collapses when a mind, something with subjective experience, actually registers the outcome. This is the von Neumann-Wigner interpretation. It was not the interpretation of a philosopher speculating loosely about physics. It was the conclusion of the most rigorous mathematical treatment of quantum mechanics that had been done to that point, arrived at through pure logic. Eugene Wigner, who shared the 1963 Nobel Prize in Physics and was one of the central figures of 20th century theoretical physics, took the argument further with a thought experiment. Suppose Wigner's friend is sealed inside a laboratory and performs a measurement on a quantum particle. From outside the lab, Wigner treats the combined system of the friend, the lab, and the particle as a quantum system. The Schrödinger equation, applied to that combined system, says it evolves into a superposition. The friend is in a superposition of saw result A and saw result B. From Wigner's perspective, until Wigner himself opens the lab and observes the outcome. But Wigner's friend, from inside the lab, would say the collapse happened the moment they performed the measurement. The particle was in a definite state from the moment they observed it. There was no superposition involving them. Who was right? When did the collapse happen? Both accounts are physically consistent within their own reference frames. They cannot both be describing the same objective reality. This is not a philosophical puzzle sitting at the edge of physics. This is a precise formal problem sitting at the center of it. And the solutions the field has developed are all, in different ways, attempts to get the same answer while avoiding the conclusion that consciousness plays a special role. Many worlds says the wave function never collapses. Both outcomes happen. Wigner and his friend are correct because they are in different branches. But many worlds requires accepting that every quantum measurement in the history of the universe created a new branch, and that all those branches are equally real, and that the totality of reality is an incomprehensibly large tree of parallel histories of which we perceive one. And it still doesn't explain why we perceive one branch rather than experiencing all of them simultaneously. Decoherence says that large objects interact with so many environmental particles so quickly that their superpositions become effectively invisible. The environment acts as a continuous measurement, suppressing quantum behavior at the macroscopic scale. But decoherence does not produce collapse. It produces something that looks like collapse from the outside, while remaining a superposition in the full description. It makes the quantum behavior hard to see without removing it. Copenhagen says the question of what is happening before measurement is meaningless. Only measurement results are physical. Do not ask about the state of the particle before measurement. This position allows you to use quantum mechanics without confronting its foundations. It is professionally convenient. It is not an explanation. What none of these fully avoids is this: if consciousness is not special in quantum mechanics, then the universe was in a superposition for hundreds of millions of years before any observers existed. Stars and galaxies are probability clouds. The early universe had no definite configuration, and when life eventually evolved and minds eventually formed, those minds somehow became the mechanism by which the universe's ancient history became retroactively definite. John Archibald Wheeler, who coined the term black hole, he collaborated with Einstein and Bohr and Feynman. He was one of the giants of 20th century physics, took this seriously. He called it the participatory universe. His claim was that the universe cannot be described without observers, because observers are not separate from the universe. They are part of the mechanism by which the universe becomes real. The universe, in Wheeler's view, brought itself into existence by evolving observers who could give it a definite past. We do not discuss this publicly because it sounds like we are claiming that human consciousness is cosmologically important. And making that claim in a scientific context risks ridicule. The social cost of being associated with mysticism is high. But consider what it would mean if Wheeler was right. If the universe brought itself into existence by evolving the observers that would give it a definite past, then the existence of life, the evolution of minds, is not a side effect of cosmic history. It is a structural necessity. The universe without observers would be a cloud of probabilities, a superposition of all possible configurations, never resolving into actual facts. We are not living in a universe that happened to produce minds. We are living in a universe that needed to produce minds in order to be a universe in any meaningful sense. This puts consciousness in a completely different position than biology currently assigns it. Neuroscience tells us that consciousness is a product of neural computation, an emergent property of sufficiently complex information processing, an output of the brain that has no special status in the physical world. The brain is made of neurons. Neurons are made of chemistry. Chemistry is made of physics. And physics is blind and mindless at its foundation. But quantum mechanics, followed honestly to where von Neumann and Wheeler and Wigner followed it, says the foundation is not blind. The foundation includes observers as a structural component. The act of observation is not a passive reception of facts that pre-exist it. It is a constitutive act. It makes facts. If this is true, then the universe needs you. Not you specifically, but minds, consciousness, observers. The universe is not a stage on which you perform. It is a system that required your existence to become definite. Whether this should comfort you or terrify you, I leave to you. The question of what collapses the wave function is still open. The von Neumann argument is still valid. The possibility that consciousness is not incidental to reality, but structural, remains on the table. We just prefer not to sit at that table. Do this right now. Point at the past. Wherever you pointed, behind you, downward, somewhere to the left, you did it without hesitation. The past has a location in your intuition. Time flows in one direction. The past is fixed. Accessible, the past is fixed. Accessible through memory. Unreachable through action. The future is open, unknown. The future is open, unknown across the place below. This feeling is more fundamental to human experience than almost anything else. More reliable than your sense of up and down, which can be fooled. More constant than your sense of self, which shifts over time. The directionality of time, the fact that causes come before effects, that memory points backward, that broken glasses stay broken, feels like the bedrock of reality. Here is what I want you to understand, clearly, without softening it. Physics does not have this. Go through the fundamental equations of physics one by one and look for an arrow of time. Newton's laws of motion. Take any trajectory, reverse the direction of every particle. The trajectory runs backward just as smoothly and consistently as it ran forward. Both are valid solutions. Maxwell's equations of electromagnetism. Time reversal produces equations that are equally valid. The Schrödinger equation of quantum mechanics. Time reversible, exactly. Einstein's field equations of general relativity. Time symmetric, with a minor exception in black hole thermodynamics. The standard model of particle physics, almost exactly time symmetric, with a tiny violation in certain weak force interactions that is far, far too small to explain the asymmetry you experience between past and future. At the fundamental level, the universe has no preferred direction of time. Forward and backward are equivalent. The equations work equally well in both directions. There is nothing in the laws of physics that says time must flow from the past to the future, rather than from the future to the past. So where does the arrow come from? The standard answer is entropy. The second law of thermodynamics tells us that in any closed system, entropy, a measure of disorder, of how many different microscopic configurations correspond to the same macroscopic state, tends to increase over time. Scrambled eggs don't unscramble. Shattered glasses don't reassemble. Buildings decay. They don't spontaneously construct themselves. These irreversible processes define a direction. They give time its arrow. And the logic works at a certain level. The scrambled egg corresponds to an astronomically larger number of possible molecular configurations than the unscrambled egg. When the system evolves randomly, it almost always moves from the small number of ordered configurations toward the enormous number of disordered ones. Not because there is any law pushing it toward disorder, but simply because there are vastly more disordered states to land in. This is why entropy increases, and this is why you experience time flowing in a direction. The past was more ordered, the future will be less ordered, and the direction from lower to higher entropy is what we experience as forward in time. Satisfying, clean, done. Except for the next question, which is, if entropy always increases, then the Big Bang must have started in a state of extraordinarily low entropy. Improbably low, almost impossibly low. The most improbably ordered state you can imagine for a universe of this size and energy. Roger Penrose, one of the most mathematically sophisticated physicists alive, has calculated this. He asked, given the current entropy of the observable universe, what is the probability that the universe began in its actual initial state, rather than a randomly selected state? The answer he got is 1 in 10 to the power of 10 to the power of 123. Let that number sit for a moment. 10 to the power of 10 to the power of 123. The number of digits you would need to write the answer is itself a number larger than the number of atoms in the observable universe. The improbability of the actual initial conditions of the Big Bang is not just large, it is a kind of large that has no precedent in any other physical measurement. We have no explanation for it. There is no equation that mandates the Big Bang to have been in a low entropy state. There is no physical principle that says the initial conditions had to be what they were. The extraordinary order of the beginning is a brute fact, observed, quantified, and utterly unexplained. And here is the implication that follows from it. The arrow of time you experience, the reason memory points backward, the reason causes precede effects, the reason you age instead of getting younger, exists only because of that improbable beginning. If the Big Bang had been in a typical high entropy state, there would be no arrow. There would be no past and future in the sense you experience them. There would be no you, because the orderly chemical processes that maintain life require a reliable direction of entropy increase. Your sense of time existing as a direction, your ability to remember breakfast but not tomorrow, to watch a glass shatter and know it won't reassemble, is entirely a consequence of an initial condition that had a probability of 1 in 10 to the 10 to the 123. Remove that accident, and you remove time. But now go deeper. Some physicists, following this logic carefully, have concluded that time may not be fundamental at all. Julian Barber, an independent theoretical physicist who has spent decades on this question, argues that the equations of physics are timeless, and that what we call time is an emergent phenomenon, a label that complex systems apply to the way they move through configuration space. In Barber's picture, there is no flow, there is no river of time carrying you from moment to moment. There is a four-dimensional, static structure, all of history, all of the future, all of every possible now, all existing simultaneously in a kind of eternal present, and consciousness is a particular cross-section of that structure that constructs the sensation of movement by comparing its own configuration to nearby configurations. You are not moving through time. Time is not moving at all. The universe is a frozen four-dimensional sculpture, and your experience of it as changing is the way a mind reads a static structure from the inside. If this is correct, then every moment of your life, every good thing, every loss, every ordinary moment of sitting in a room exists permanently, not as a memory, as a real, contemporaneous fact in the block of four-dimensional space-time. The past is not gone, it is just elsewhere in the block, as real as you are, as present as you are, permanently inscribed. Your lost loved ones exist, not as a consolation, as a physical fact, if Barber is right. The version of you from 10 years ago exists, right now, equally real, at a different coordinate in the block. The moment of your death is there, already, waiting at a coordinate you will arrive at. Now think about what it means to grieve in this picture, to miss someone who died. In the standard model of time, they are gone. Their existence has ended. The river has moved on, and they are no longer in it. The loss is absolute. But in the block universe, the person you grieve is still there. They exist at a specific set of coordinates in four-dimensional space-time. Every moment they were alive is still real, is still happening in the block, is still as present as your present moment. The relationship between you and them still exists, inscribed permanently in the structure of space-time. This does not change the fact that you cannot visit those coordinates. You are locked into the leading edge of your own world line, moving forward in the block, the way a needle moves along a record groove, unable to go back. The grief is real. The loss, from the perspective of your lived experience, is real. But the thing you lost is not gone. It is elsewhere. The block universe does not make loss less painful, but it changes its character, from absolute erasure to permanent separation, from ending to inaccessibility. Whether that is better or worse, I leave to you. The clock is not measuring a flow. The clock is a brain drawing direction on a structure that has no intrinsic direction. The arrow of time is a story you tell about something that at the deepest level has no arrow. This one starts as mathematics and ends somewhere that most people prefer not to go. In 1890, Henri Poincaré proved a theorem in the mathematics of dynamical systems. The theorem says, if you have a physical system that is bounded, finite in space, finite in energy, finite in the number of its configurations, and if you let it evolve for long enough, it will return to any previous configuration. Not approximately, exactly. Given sufficient time, every finite physical system will revisit every state it has ever been in. This is the Poincaré recurrence theorem. It is rigorously proven. It is not controversial in mathematics. And its implications for an eternal universe are deeply strange. Our observable universe contains roughly 10 to the power of 80 particles. The number of meaningfully distinct configurations of those particles is astronomical, a number so large that representing it requires multiple layers of exponentiation. But it is finite. If the laws of physics are deterministic, and the universe has finite phase space, the number of distinct configurations is finite. The timescale for a full recurrence, the time it would take for the universe to cycle through all possible configurations and return to its current state, is so enormous that the current age of the universe, 13.8 billion years, is essentially zero relative to it. The recurrence time for a system the size of our observable universe is a number you cannot write down in this universe with conventional notation. But here is the question: is time finite or infinite? If the universe expands forever, which current observations of dark energy suggest is likely, then time does not end. The universe does not collapse. It continues expanding, cooling, dimming, until all the stars have burned out, and all the black holes have evaporated, and all the matter has decayed, and then it continues as an empty, expanding space for much, much longer, and then longer still. The dark energy model says time goes on without limit. If time is infinite, then the Poincaré recurrence time will eventually be reached. Every configuration the universe has ever been in will recur, including the configuration it is in right now, including you in this exact state, reading these exact words, with every memory you currently have and every thought you are currently thinking. You will exist again, not someone like you, not a descendant. You, because you are your configuration, the specific arrangement of matter and energy that produces the experience of being you. If that configuration recurs, the experience recurs, with no awareness of the gap between iterations, no memory of the previous loop, no sense of repetition. Each time will feel like the first time. Each time you will sit here and feel like you are reading this for the first time. And again after that. And again after that. Infinitely. You are not living a life with a beginning and an end. You are living a cycle that has already run countless times and will run countless more times. And each time through, you will believe it is the first time, because the recurrence includes the belief that it is the first time. Nietzsche described this as the heaviest possible thought, that everything will repeat, exactly, forever. He meant it as a philosophical test. The mathematics says it may be literally true. But the same mathematician who developed the foundations of this framework, Ludwig Boltzmann, who built statistical mechanics in the 19th century, noticed something even more disturbing lurking inside it. If the universe can spontaneously fluctuate back to low entropy states given infinite time, then the question becomes, what is the most likely spontaneous fluctuation to produce a given phenomenon? And the answer is always the simplest one. Always the minimum amount of structure required. A full universe, with billions of years of real physical history actually occurring, is an extraordinary complex thing. It requires an enormous sustained fluctuation. Not just a momentary arrangement, but a whole sequence of states, maintained consistently for billions of years, enough to produce galaxies and stars and planets and life. A single brain, floating in thermal noise, with false memories of a history that never occurred, is vastly simpler. The amount of information required to specify a brain with coherent memories is enormous, but it is much less than the amount required to specify an entire universe with a real history. And in statistical mechanics, simpler things are more probable. This is the Boltzmann brain problem, and it is one of the most serious technical embarrassments in modern cosmology. The mathematics of eternal universes, the mathematics implied by current cosmological models, predicts that spontaneous fluctuations producing isolated brains with false memories are overwhelmingly more common than genuine observers in genuine universes with genuine histories. For every real observer, like you, presumably, reading this in an actual room with actual history, the statistics suggest there are vastly more Boltzmann brains, momentary fluctuations into coherence, experiencing a hallucinated reality for a brief moment before dissolving back into thermal equilibrium. If this is correct, and if you accept the mathematical framework that leads to it, then the probability that you are a genuine observer in a genuine universe is extraordinarily small. The probability that you are a Boltzmann brain, briefly flickering into existence, experiencing a coherent moment, about to dissolve, is vastly higher. You cannot prove you are not. The experience of being a Boltzmann brain, in its brief coherent moment, would feel exactly like the experience of being a real person in a real room. The coherence is real while it lasts. The memories are internally consistent. There is no phenomenological difference between genuine experience and hallucinated experience from the inside, and the mathematics says the hallucinated version is more common. Every cosmological theory that predicts an eternal future has this problem. If your theory predicts that Boltzmann brains outnumber real observers, your theory has predicted that most observations made in your universe cannot be trusted, which means your theory cannot be empirically verified, which means your theory has made itself useless. Most cosmological theories do predict eternal futures. We do not have a solution to the Boltzmann brain problem. We have the practice of assuming we are real observers and moving on, which is precisely what a Boltzmann brain would do. But here is the deepest version of the problem, the one that most treatments leave out. It is not just that Boltzmann brains are more probable than real observers in an eternal universe. It is that the entire scientific project depends on observers being reliable. Observations are how we test theories. If most observers are hallucinating, most observations cannot be trusted. Which means the observations we used to establish that the universe is eternal, the very observations that create the Boltzmann brain problem, are themselves potentially unreliable. The theory undermines the observations that confirmed it. It is self-defeating. The physicist's standard response is pragmatic. If we assume we are Boltzmann brains, science becomes impossible, so we must assume we are not, and move on. This is reasonable as a working posture. It is not an answer. It is a decision not to ask the question.
The question remains, why does the universe preferentially produce large, structured, complex observers with genuine histories rather than minimal fluctuations? What is the mechanism that tips the statistics away from Boltzmann brains and toward real minds in real universes? We do not know. We have not found it, and the mathematics, left to itself, keeps pointing the wrong way. Let me describe what the universe should look like on very large scales. On large scales, much larger than any individual galaxy, much larger than any galaxy cluster, the universe should be smooth, homogeneous, isotropic. This is called the cosmological principle, and it is one of the foundational assumptions of the standard model of cosmology. It means there are no special places, no preferred directions, no enormous structures that dominate the landscape. Matter is distributed more or less evenly throughout, and gravity produces local clustering, galaxies, clusters, superclusters, but these structures are embedded in a uniform background. Zoom out far enough, and the universe looks the same in every direction. In this picture, on the very largest scales, galaxies drift apart with the expansion of the universe. Clusters of galaxies feel each other's gravity and move around each other locally. But there should be no coordinated large-scale flow, no single direction that everything is streaming toward, no invisible source outside the observable universe that is pulling the whole structure in one direction. In 2008, a team of researchers at NASA, led by Alexander Kashlinsky, analysed the motion of galaxy clusters across the sky. They were using a specific technique, a refined version of the kinematic Sunyaev-Zeldovich effect, that allowed them to measure the velocity of distant clusters in a way it was independent of distance estimates. This is important because distance measurements are often uncertain. This technique gets at the real bulk motion more directly. What they found was that hundreds of galaxy clusters, spread across billions of light years, were all streaming in the same direction, not drifting randomly as the cosmological principle would predict, not moving according to the gravitational influence of visible structures, which the team had carefully accounted for, moving coherently all toward the same patch of sky at nearly 2 million miles per hour. They called it dark flow. The scale of the coherence is what matters. Individual galaxy clusters moving under local gravitational influences is expected. Galaxy clusters in our local neighbourhood being pulled toward the great attractor, a known mass concentration about 250 million light years away, is expected and observed. But a coherent flow of hundreds of clusters spanning billions of light years, directed toward a single point, cannot be explained by any structure we can see inside the observable universe. The mass required to produce a gravitational pull this consistent, this strong, and this coherent across this volume of space would have to be located
outside our observable horizon. Something beyond the edge of what we can see, beyond the sphere from which light has had time to reach us, is massive enough to exert a detectable gravitational influence on everything inside our observable universe. Think about what this does to the cosmological principle. If dark flow is real, then the universe beyond our horizon is not more of the same. It contains a structure, a concentration of mass, or a region of different physics, or something we do not have a name for, that is large enough and dense enough to produce a coherent gravitational effect on a volume of space 93 billion light years across. The universe does not look the same in every direction on the largest scales. There is a preferred direction. There is something out there beyond everything we can see that is shaping everything we can see. The mainstream response has been cautious, skepticism. Some analyses of the same underlying data found weaker or absent signal. The result has been contested. Kashlinsky and colleagues have published follow-up analyses maintaining the detection. The debate continues. But here is what the mainstream has not done, and what I want to draw your attention to. Even in the analyses that find the signal, the mainstream has not seriously asked, what would have to be true about the universe beyond our horizon to produce this effect? The answer to that question is extraordinary. The size and mass required, the scale of structure needed outside our horizon to pull everything inside it in one direction, would violate the cosmological principle dramatically. It would mean the universe we can see is not representative of the universe that exists. We are in a region that is being influenced by something we will never directly observe, something whose nature we cannot determine, something that our standard model has no framework to describe. Then there's an even more radical possibility. The pull might not be from a mass concentration at all. It might be from a neighbouring region of space with different vacuum energy, a bubble in a multiverse structure, where the laws of physics differ from ours. Or it might be from a region whose geometry differs from ours, where space itself is curved differently. We are falling toward the dark. The dark is outside everything we can see. And the sound of the pull, the coherent motion of hundreds of galaxy clusters, is the only evidence we have that something is there. Now, here is the uncomfortable implication that nobody draws out explicitly. The cosmological principle, the assumption that the universe is homogeneous on large scales, is not just a convenient simplification. It is load-bearing. The entire mathematics of the standard cosmological model is built on it. The equations that describe how the universe expands, how structure forms, how the cosmic microwave background behaves, all of them assume homogenation. Remove it, and you cannot solve the equations. You do not have a model. If dark flow is real, you need a different model, not an updated version of the current one. A fundamentally different one, built on foundations that allow for large-scale anisotropy, for the universe to have a preferred direction on the very largest scales. Building that model requires first admitting that the current model has a foundational problem. And admitting that is uncomfortable, for the same reason it is always uncomfortable when a foundational assumption fails. Everything built on top of the assumption becomes uncertain. Every cosmological measurement that was interpreted using the assumption of homogeneity would need to be reinterpreted. The age of the universe, derived from the expansion rate measured under the assumption of isotropy. The distribution of dark matter, inferred from the pattern of galaxy clustering, assumed to be isotropic. The nature of dark energy, characterized using an isotropic expansion model. All of it would need to be revisited. This is not the work of a few papers. It is the work of a generation, and the mainstream has concluded, reasonably, even defensibly, that dark flow is not well enough established to justify initiating that work. But the alternative is to sit on a foundational assumption that might be wrong, and to keep building on it, and to keep reinterpreting data through it, and to let the anomaly sit in the literature as a known oddity, while the evidence for it neither resolves nor disappears. We have been doing that for 15 years. At some point, the anomaly demands a reckoning. Here is the standard story of life. The solar system formed about 4.6 billion years ago from a cloud of gas and dust collapsing under its own gravity. The Earth formed from the debris around the young sun, a process of accretion and collision that took millions of years. For the first several 100 million years, the Earth was geologically violent, bombarded by asteroids, reshaped by volcanism, mechanically harsh. Then, around 3.7 to 3.8 billion years ago, the first simple microbes appeared. Life started here, from scratch, using the chemistry available on the early Earth, through a process we call abiogenesis. This story is what everyone is taught. It is the framework for astrobiology. It drives the search for life on Mars, because if life started here spontaneously, it might have started there too. It drives the study of extremophiles, because if life can survive harsh conditions here, it can survive them elsewhere. The story has a problem. The problem is the chemistry. The origin of life, the transition from non-living chemistry to self-replicating biology, requires a sequence of chemical steps. The most widely accepted current model is the RNA world hypothesis, the idea that before DNA and proteins, there was RNA, a molecule that can both carry genetic information and catalyze chemical reactions. RNA first, then DNA and proteins as evolutionary refinements. To make RNA from scratch under realistic early Earth conditions requires producing nucleotides, the building blocks of RNA. To make nucleotides, you need a sugar, a phosphate group, and a nitrogen base, assembled in the right order, under the right conditions. Each precursor requires its own chemical pathway. Getting them to react together requires specific conditions. Getting the resulting nucleotides to link into chains, to polymerize into RNA, requires removing water, which is chemically difficult. Bond, chaos. Bond. Researchers at the Sutherland Group in Manchester, at the Shostak Lab at Harvard, at other institutions, they have worked out specific chemical pathways for individual steps. Progress has been real and significant. But progress in a controlled laboratory is not the same as plausibility on the early Earth. In a laboratory, you work with purified reagents, you control pH and temperature, you sequence the reactions, you prevent competing pathways from interfering. The early Earth did none of these things. The early Earth was a globally distributed, chemically heterogeneous, UV-irradiated environment where the same radiation that drives productive chemistry also destroys organic molecules, where the same water that enables biology also hydrolyzes the bonds that connect RNA monomers, where there was no separation between constructive and destructive processes. Getting from the chemistry of the early Earth to a self-replicating RNA molecule in the absence of any guiding intelligence, without controlled conditions, with all the competing reactions happening simultaneously, is a problem that becomes harder the more carefully you examine it, not easier. Francis Crick, the co-discoverer of the double helix structure of DNA, one of the central figures of molecular biology in the 20th century, looked at this problem in the 1970s and concluded that spontaneous abiogenesis on Earth in the available time was implausible. He proposed directed panspermia, the intentional seeding of Earth by an extraterrestrial intelligence. Most researchers consider this specific proposal far too speculative. But Crick's underlying technical concern, that the chemistry of life's origin is harder than it looks, is shared by more researchers than are willing to say so publicly. And here is where the data from astronomy becomes relevant. The Murchison meteorite fell in Australia in 1969. When researchers analysed it, they found more than 90 amino acids, the building blocks of proteins. More than 20 of them are found in terrestrial biology. They found nucleobases, the components of RNA and DNA. They found sugars, complex organic molecules synthesized by the chemistry of the interstellar medium, preserved inside a rock that formed in the early solar system, delivered to Earth from space. This was not an isolated finding. We have now found complex organic molecules in dozens of meteorites, in comets, analyzed by spacecraft, in the molecular clouds between stars, in the atmosphere of Saturn's moon Titan. The Rosina instrument on the Rosetta mission, which orbited Comet 67P Churyumov of Gerasimenko, detected glycine, the simplest amino acid, directly in the comet's coma. We have found the precursors of biology distributed throughout the cosmos. The chemistry of life is not rare. The universe is drenched in organic molecules. Carbon and hydrogen and oxygen and nitrogen, the elements of life, are among the most abundant in the cosmos, and they combine naturally into complex organic structures wherever they encounter radiation and temperature gradients. Now put the two pieces together. If the chemistry of life is common throughout the cosmos, but abiogenesis on a single planet under realistic conditions is as difficult as the evidence suggests, then the most likely conclusion is one the mainstream is reluctant to state directly. Life probably did not start on Earth in the conventional sense. Life is a cosmic process. The molecules that constitute terrestrial biology arrived here with a history, partially processed, already organized to some degree, coming from an environment, the interior of comets, the surfaces of asteroids, the dense molecular clouds of the interstellar medium. That is cold, the fat is called, the wild science can hang and carry out on the stages of the asteroids. If life predates the solar system, if the molecules of biology were already on their way to complexity before the Earth formed, then the question, how did life begin on Earth, is incomplete. The question is, where was life going before it arrived here, and how long had the journey been underway? Universe is 13.8 billion years old. The solar system is 4.6 billion years old. There were 9 billion years of cosmic chemistry before the Earth existed. 9 billion years of organic molecules being synthesized in molecular clouds, processed in protoplanetary disks, delivered to planetary surfaces, seeded across the galaxy by collisions and ejections and stellar winds. 9 billion years of the universe doing chemistry with the raw materials of biology before our planet was even a thought. life may be as old as the stars that made the elements that life is made of. It may be woven into the fabric of the galaxy at a level we have barely begun to investigate. And if that is true, the silence of the sky looks different than it did before. If life is a cosmic process that has been running for billions of years across the galaxy, if the chemistry of biology is a natural product of stellar and interstellar chemistry that seeds itself widely, then the question is not, why haven't we found extraterrestrial life yet? The question is, where isn't it? The silence, the great silence of the sky, the absence of detected signals, the emptiness of the cosmic background, becomes harder to explain, not easier, in a universe where life is a widespread and ancient process. If life has had 9 billion years before the solar system formed to spread through the galaxy, if it arrived here from elsewhere, then where did it come from? What happened to whatever was there before? Why has nothing reached us? The silence in this picture is not the silence of emptiness. It is the silence of something that hasn't spoken yet, or something that has fallen silent, or something that speaks in a language we haven't learned to hear. Either way, the question becomes not are we alone, but why does it seem that way, given that we probably aren't? That is a more disturbing question than the one we usually ask, because the answer to are we alone could be yes, and that's just statistics. The answer to why does it seem that we're alone, given that we probably aren't, requires something to have happened, something that explains the silence of a universe that should be speaking. And a list of things that could produce that silence without producing the silence of total extinction is short and uncomfortable to look at directly. In April 2019, the Event Horizon Telescope released the first image of a black hole, a supermassive object at the centre of the galaxy M87, 55 million light-years away, a blurry orange ring around a dark central shadow. People stared at it with something between awe and recognition. We had predicted these objects for a century. Now we could see one. What the image could not show, what no image in any wavelength, and the foundational contradiction sitting at the heart of our understanding of these objects. A contradiction that has been formally recognised for 50 years, has inspired thousands of papers from the most brilliant theoretical physicists alive, and has not been resolved. The black hole information paradox. When matter falls into a black hole, information falls with it. In physics, information means the complete quantum mechanical description of a system, the precise state of every particle, every quantum number, every detail that distinguishes this collection of matter from any other. This information, according to general relativity, cannot escape the event horizon. The event horizon is a one-way surface. Once matter crosses it, no signal, no particle, no information can come back out. The matter and its quantum description are gone from the external universe. In the 1970s, Stephen Hawking showed that black holes are not completely permanent. Quantum mechanical effects near the event horizon cause the black hole to radiate, to emit thermal radiation, now called Hawking radiation. It carries energy away from the black hole. The radiation is slow, temperature is low, and for any astrophysical black hole, the total evaporation time vastly exceeds the current age of the universe. But eventually, given enough time, the black hole loses all its mass and disappears. Now here is the problem that Hawking himself spent the rest of his life wrestling with. Hawking radiation is theoretical. It is random. Its statistical properties are determined only by the mass, charge, and angular momentum of the black hole, nothing else. Whether you throw a proton into the black hole or a complete copy of the Library of Alexandria, the Hawking radiation looks the same. The specific quantum information about what fell in is not encoded in the radiation that comes out. When the black hole evaporates and disappears, that information is gone. And quantum mechanics says information cannot be destroyed, ever. This is not a preference or an interpretation. Unitarity, the formal mathematical principle that the total probability is conserved in quantum evolution, which means that quantum evolution is reversible and information is always in principle recoverable, is one of the foundational axioms of quantum mechanics. Remove it, and the entire predictive structure of quantum mechanics collapses. Quantum mechanics works because it is unitary. If a black hole violates unitarity, quantum mechanics is broken at a fundamental level. General relativity says information falls in and doesn't come out. Quantum mechanics says information cannot be destroyed. Both theories are extraordinarily well tested, each in its own domain. And they flatly contradict each other in the one situation where both are relevant simultaneously. You might think, fine, one of them is wrong in extreme conditions. We fix it eventually. Problem solved. The problem is that we do not know which one is wrong or how it is wrong. We do not have a framework for understanding what happens inside a black hole that is consistent with both theories. We have two masterpieces of physical theory, and they give contradictory answers about the most extreme environments in the universe. The proposals have been extraordinary. The current leading approach involves holographic encoding, the idea that information is somehow imprinted in subtle quantum correlations between early and late Hawking radiation, scrambled into a form that is practically unrecoverable but formally still present. The black hole does not delete information. It encrypts it so thoroughly that decoding it would require a computation taking longer than the current age of the universe. But it produces what is called the firewall paradox, discovered by Ahmed Elmhiri, Donald Marolf, Joseph Polchinski, and James Sully in 2012. If information comes out encoded in early Hawking radiation, then by the rules of quantum information, the late radiation must be entangled with the early radiation. But quantum mechanics also requires the late radiation to be entangled with the modes just inside the event horizon, the ones it was created from. And quantum entanglement is monogamous. A quantum system cannot be maximally entangled with two different systems simultaneously. The mathematics produces a direct contradiction. Something has to give. Either the entanglement with early radiation is wrong, in which case information is not coming out and quantum mechanics breaks, or the entanglement with the interior is wrong, in which case an infalling observer crossing the event horizon hits the wall of high energy radiation and is instantly destroyed. The firewall paradox says that either quantum mechanics breaks or general relativity breaks, not at the singularity deep inside the black hole, which we already knew was problematic, but at the event horizon, the boundary of the black hole, which was supposed to be smooth and unremarkable from general relativity's perspective. One of the most fundamental predictions of general relativity, the equivalence principle, Einstein's cornerstone. The idea that a freely falling observer in a gravitational field experiences no locally detectable force breaks down at the event horizon of every black hole in the sky, if the firewall argument is correct. We do not know how to fix this. More than a decade after the firewall paradox was published, we do not have a consistent theory of quantum gravity that resolves it. And there is a layer below the firewall paradox that is even more fundamental. The fact that the two theories contradict each other in black holes is not just a practical problem, it is a signal. When two extraordinarily well-tested theories produce contradictory predictions in a specific regime, it means that regime contains physics we haven't understood yet. Physics that, when we finally understand it, will change something about both theories. We know this because it has happened before. At the beginning of the 20th century, Newtonian mechanics and Maxwell's electrodynamics were both extraordinarily well tested in their respective domains. They also contradicted each other when applied to the motion of light. The resolution was not to patch one of them. It was Einstein's special relativity, a completely new framework that contained both his limiting cases and revealed that the concepts of space and time themselves needed to be revised. The contradiction between general relativity and quantum mechanics and black holes is analogous. The resolution will not be a patch. It will be a new framework, quantum gravity, that contains both his limiting cases and reveals that some concept we currently treat as fundamental needs to be revised. Space, time, information, causality. We don't know all of them, but the black holes are telling us something needs to change. Every one of them, in every galaxy in the sky. They are all running the same experiment, the one where our two best theories disagree, and they are all getting the same answer that we don't know how to read. We have imaged two black holes. We have heard dozens of them collide, their gravitational waves shaking detectors by less than 1/10,000th the diameter of a proton. They are real, and they are telling us something. We just don't understand what they are saying yet. Let me give you one specific number, and let it do the work. The cosmological constant, the energy density of empty space, is responsible for the accelerating expansion of the universe. Quantum field theory, which correctly describes the behavior of particles to extraordinary precision, in every other context, predicts a specific value for this constant. The prediction comes from rigorous calculations accounting for every known quantum field. The measured value is approximately 10 to the minus 122 in Planck units. The predicted value is approximately 1 in those same units. The prediction is wrong by a factor of 10 to the 122 zeros. This is not a minor discrepancy. This is the largest quantitative error ever made in any scientific prediction, in any field in the history of science. Nothing else comes close. If the cosmological constant had anything near its predicted value, the universe would have expanded so explosively after the Big Bang that no structures could ever have formed. Galaxies, stars, planets, atoms, all of it would have been dispersed before gravity could pull anything together. The universe would have been an empty, rapidly expanding gas with no future worth discussing. The universe has the measured value essentially zero compared to the prediction, and consequently exists. Something is cancelling out nearly all of the enormous predicted vacuum energy to a precision of 122 decimal places, leaving behind only the tiny residual that drives the slow current expansion. We have no mechanism for this cancellation, no symmetry, no physical principle, no theory predicts why the vacuum energy should be almost exactly zero. The cancellation is precise to over 100 decimal places, and we cannot explain a single one of them. Add to this the strong nuclear force. If it were roughly 2% stronger, the Big Bang would have converted almost all hydrogen to helium in the first few minutes, eliminating the fuel for sun-like stars and eliminating the primary ingredient of water. If it were roughly 5% weaker, protons and neutrons would not bind into nuclei. No stable atoms would form. Add the electromagnetic force. The ratio of its strength to gravity determines the size and lifetime of stars. Change it by a few percent, and stars either burn out too quickly to warm planets for long enough, or their radiation prevents planets from forming at all. Add the initial density fluctuations of the Big Bang, the slight over and under densities that seeded all structure. These had to be tuned to roughly 1 part in 100,000. Too smooth, and gravity never forms galaxies. Too rough, and the universe collapses into a sea of black holes before stars form. Add the ratio of baryonic matter to dark energy in the universe, each of which has to fall within specific ranges for the universe to develop structure. Add the mass of the Higgs boson, which determines the mass of all other fundamental particles, which has to be in a specific range for atoms to be stable. Add a value of Planck's constant and Newton's constant and the fine structure constant. Go through the list. Most of the fundamental constants sit in narrow ranges that permit complexity. Small variations that would seem trivial compared to the enormous possible range of values each constant could in principle take, produce universes with no atoms, or no stars, or no carbon, or no time for anything interesting to happen. The probability of randomly selected constants producing a life-permitting universe, given the enormous parameter space, is extraordinarily small. The universe looks, from outside, like a system that was adjusted. 3 serious responses exist. The multiverse. There are infinitely many universes with different constants, and we are in this one because only life-permitting universes contain observers. The fine-tuning is real, but not meaningful. It is selection bias. This is logically valid. The other universes are unobservable. The multiverse explains the fine-tuning by positing an infinity of realities we cannot verify. The final theory, perhaps the constants are not arbitrary, but uniquely fixed by some deep principle of mathematical consistency. Perhaps there is only one logically possible physical universe. String theory was hoped to be this theory. Instead, it produced 10 to the 500 possible consistent solutions, the string landscape, which makes the problem worse. Design. An agent set the constants. Not scientific, not falsifiable, but it takes the fine-tuning most literally. None of these is satisfying. The mainstream prefers the multiverse as the least uncomfortable option, while acknowledging it is untestable. The fine-tuning remains real. The explanation remains missing. But here is what I want you to notice about all 3 options. The multiverse says there are infinitely many universes, and we are in one that permits life because only life-permitting universes have observers to notice they permit life. This is a valid logical move, but it requires accepting an infinite number of unobservable realities. It requires accepting that science, which is built on the principle that theory should be empirically testable, is explaining our universe by invoking an infinite number of universes we can never test. The multiverse is the scientific version of saying everything that can happen does happen, and then noting that given that premise, our universe is unsurprising. The premise does all the work, and the premise is not testable. The final theory option says, perhaps there is a deep mathematical structure that uniquely determines the constants. Perhaps the universe couldn't have been any other way. This is appealing. It is what many physicists hope for. But string theory, the most developed attempt at a final theory, has instead produced the landscape, 10 to the 500 possible consistent solutions, none preferred. Instead of finding that the constants are uniquely determined, we found that they might be arbitrarily selected from an enormous space of possibilities. The search for the final theory has, so far, made the fine-tuning problem worse. The design option is not scientific, but it is worth being honest about why. The design option is rejected, not because the evidence contradicts it. The fine-tuning is exactly the kind of evidence you would expect if the constants were set intentionally. It is rejected because it is not falsifiable, and because it does not explain the designer. It trades one unexplained thing, the fine-tuned constants, for a different unexplained thing, the agent who fine-tuned them. It is an explanation that generates another question of the same type, rather than resolving the type. None of the three options is a genuine explanation. All three of them are reframings. They change the way the question is asked, without answering what is being asked. We live in a universe configured for our existence with a precision no known physics can account for. That fact is sitting on the table. We keep looking away from it, but it doesn't move. Every black hole forming in our universe might be opening a new universe, not as metaphor, as the literal physical prediction of a specific, mathematically rigorous framework. Standard general relativity predicts that matter collapsing into a black hole ends at a singularity, a point of infinite density where the equations break down. This is universally understood as a sign that the theory is incomplete. Infinite density is not physical. It is the theory's way of saying, beyond this point, I cannot help you. A more complete theory of quantum gravity would replace the singularity with something physical. In a framework called Einstein-Cartan theory, one candidate for that replacement is a bounce. When collapsing matter reaches extreme density, quantum torsion effects, ignored in standard general relativity, generate a repulsive force that reverses the collapse. The matter bounces. In the reference frame of the bouncing matter, the reversal looks like an expansion. A new region of space-time begins to expand. From inside that expanding region, the expansion looks like a Big Bang. Nikodem Poplovsky at the University of New Haven developed this framework carefully and published his results in peer-reviewed journals. The framework is mathematically consistent. It resolves the singularity problem, and its central prediction is that our Big Bang was the interior of a black hole that formed in some parent universe. This does not mean we are near anything dangerous. From inside the universe born in a black hole, the universe is just a universe, expanding, full of matter, operating according to consistent physical laws. The event horizon of the containing black hole corresponds, in cosmological terms, not to a nearby boundary, but to what we call the cosmological horizon, the edge of the observable universe, the limit beyond which light hasn't reached us. We are not approaching a wall. We are living in the stable interior of a region that formed from a collapse we cannot access. Lee Smolin, whose technical contributions to theoretical physics include foundational work on loop quantum gravity, extended this idea into a full cosmological framework he called cosmological natural selection. The proposal is this: if black holes create child universes with laws slightly different from the parent, then the universe is essentially a reproducing system. Universes that form many black holes have many descendants. Universes that form few black holes have few descendants. Over many generations, the population of universes shifts through a process analogous to natural selection toward universes optimized for black hole production. What does a universe optimized for black hole production look like? It has the right kinds of stars, Massive stars that exhaust their fuel quickly collapse and form black holes. Those stars require the physical constants to be in specific ranges. And here is the key. A universe with stars of the right mass to produce black holes also has stars that produce the long-term stable environments in which planets form around smaller, longer-lived stars. Chemistry becomes possible. Biology becomes possible. The fine-tuning problem looks different in this framework. The constants of nature are not randomly drawn from an infinite lottery. They are not designed by an agent. They are the product of a selection process, a Darwinian pressure operating at the cosmological scale, filtering over billions of generations of universe formation for the ability to produce more universes. We inherited our constants from a lineage that was repeatedly selected for black hole producing capacity. Those same constants produce everything else we see. Smolin has made this testable in a way that generic multiverse theories cannot be. He predicts that any variation in the fundamental constants that increases black hole production should also increase the hospitality of the universe to complexity, and any variation that decreases black hole production should decrease it. This prediction can be checked against what we know about stellar physics, and is not obviously violated. There is one specific prediction worth highlighting. If cosmological natural selection is correct, the massive neutron stars, the maximum mass before they collapse to black holes, should be near a value that maximizes black hole production. Too low and most neutron stars collapse immediately, producing too many black holes too quickly and disrupting the galaxy. Too high and few neutron stars produce black holes at all. The theory predicts we should find ourselves near the peak, and the observed maximum neutron star mass, around 2 solar masses, is in the range the theory predicts. This is not proof, it is one prediction among several that the theory makes. But it is the kind of quantitative prediction that distinguishes a serious scientific proposal from a philosophical speculation. Cosmological natural selection makes predictions. They have not been falsified. The mainstream's reluctance to engage with it is not a consequence of the theory failing tests. It is a consequence of the theory being strange. It is strange because it implies that the universe is, in a loose sense, alive. Not conscious, not purposeful in a mystical sense, but reproductive. It creates copies of itself. Those copies are selected by a process that filters for specific properties. The properties that survive the selection are the ones we observe. This is Darwin applied to cosmology, and the reason it makes people uncomfortable is not that the evidence is against it, but that the analogy is too close to biology for comfort. Physicists prefer their universes to be inert. But step back from the technical details. Look at the full picture. If this framework is correct, then the universe you live in is one generation in a lineage, a specific generation, with specific ancestors and specific descendants. Your universe was born from the collapse of a star in a parent universe, a universe you can never visit, governed by laws similar but not identical to yours. The parent universe was born from a collapse in a grandparent universe. The lineage extends backward through generations we have no access to, toward a first universe that was not born in a black hole, but emerged from whatever came before. And at this moment, in your universe, the lineage continues. Every massive star in every galaxy that has exhausted its fuel and is collapsing is opening a door. A new space-time is beginning, a new expansion. A new universe, with constants slightly different from yours, starting its own journey. The black holes visible in your sky are not graves. They are births. Not metaphorically, physically. They are the mechanism by which the universe reproduces. They are the most important objects in the cosmos. not just because of their role in galaxy formation and stellar evolution, but because they are the reproductive organs of space-time itself. You are not at the beginning of anything. You are not at the center. You are a descendant of a long lineage, living inside a universe that is itself the descendant of a long lineage, participating through the stars in your sky, forming and dying, in the production of descendants you will never see. The universe is not a place, it is a genealogy, and the black holes in the night sky are the moments when the genealogy adds a new branch. 10 theories, 10 places where the mathematics is real, the data exists, and the mainstream is quiet. Look at what they have in common. Every one of them follows the logic, honestly, and arrives somewhere the standard narrative didn't prepare you for. Every one of them puts something we assumed was stable, the existence of matter, the constancy of light, the objectivity of observation, the direction of time, the uniqueness of our universe, up for serious reconsideration. And every one of them, if correct, changes not just a calculation, but the story. Not just an equation, but what we are. Not just a model, but where we stand in relation to everything else. We are rounding errors, survivors of an asymmetry our best theory cannot explain. We may live under laws that were different at the beginning and might vary elsewhere. We may participate, through the act of observation, in making the universe real. We experience time as directional because of an improbably ordered starting point that had a probability of essentially zero. We may be living a loop that has run countless times and will run countless more times, each iteration indistinguishable from the first. We may be falling toward a structure outside everything we can see. We may have inherited our biology from chemistry that predates our solar system by billions of years. We live in a universe whose most extreme objects contain a contradiction between its two best theories. We inhabit a universe configured for our existence with a precision no known physics explains. And we may be one generation in a long lineage of universes born from collapse we cannot visit, making descendants we will never see. These are not questions at the edges of knowledge. They are questions at the center. The silence around them is real. Not conspiratorial, no one is hiding this. Not dishonest, the papers are public, the arguments are available. The silence is institutional and social and understandable. Science is a human enterprise, and humans prefer stable foundations. Questioning the foundation threatens the building. And the building has produced antibiotics, semiconductor chips, gravitational wave detectors, vaccines, and the ability to photograph black holes 55 million light years away. The building is worth protecting, but the foundation is worth examining. And the examination reveals that the most important questions, the ones about why matter exists, what time is, what observing does to reality, where life came from, whether our universe is one of many, whether the laws of physics are truly universal, are open. Not almost solved, not mostly understood, open. You deserve to know that. Not so you can be nihilistic about it, not so you can feel crushed by the uncertainty, but so you can walk through the world with an accurate map of what is known and what isn't, because the map matters. Knowing where the territory ends and the blank space begins is not disorienting, it is clarifying. It is the difference between a person who thinks they understand everything and is confused when things don't fit, and a person who knows where the boundaries of understanding are and is therefore prepared when the boundaries move. The boundaries are about to move. The anomalies are accumulating. The Hubble tension is real. The JWST galaxies were too big too early. The muon wobbles at the wrong speed. The data keeps producing surprises. The paradigm is under pressure. When it shifts, and it will, the 10 questions we discussed tonight will not be fringe concerns. They will be central. The new textbooks will be organized around them. The new generation of physicists will be trained to take them seriously. If there is, something is happening. For now, they live in the silence. You know they are there. That is not nothing. That is the beginning of the kind of thinking that makes real progress. Not accepting the official story uncritically, not rejecting it wholesale, but knowing which parts are solid and which parts are held together by institutional inertia and collective preference for comfortable foundations. The universe is stranger than you were told. Stranger, and, if anything, more worth understanding. Not because the strangeness is reassuring, it isn't, particularly, but because the strangeness is real, and real things deserve honest attention. Go look at the sky tonight, at the black holes eating stars at the centers of galaxies, possibly opening new universes inside themselves. At the stars whose carbon was cooked in stellar cores and scattered by supernovas, and may have been assembled into life somewhere before it arrived here. At the ancient light that crossed 13 billion years of expanding space to reach your eye and collapsed a wave function in your retina that may, in some framework we haven't settled yet, have required your mind to happen. You are a rounding error that learned to ask questions. That is the most extraordinary thing in the universe.